Welcome viewers in my lecture on multi-dimensional unconstrained optimization. In my previous lecture we have discussed about single variable function, I mean single dimensional optimization technique. In this lecture I will cover multi-dimensional unconstrained optimizations. In fact, real life problems are not a single valued functions. Suppose any if you consider any functions, any real life problems that consist of many variables. Say for example, when I am coming to my office, if my objective is to reach the office in perfect time, then there are so much variables in terms of say congestion in the road, condition of my car, so much in right time, whether I have started from my office, provided there is no jam in the road. So real life problem is really multidimensional and complex in nature. There is no single variable function in real life. Say for example, in our productions, say for I want to get a best product from my machine, and generally with the mechanical engineers is considered the primary or basic input parameters are basically speed, say for example speed, feed and depth of cut, say depth of cut, depth of cut. So if my function is to, if my function is say for example, if my function is consists of speed, feed, if this one is feed, I mean okay, feed and depth of cut, DOC say, and the output is say for quality of the product, okay. So this is called multi-dimensional, multi-variable or multi-dimensional variable or multi-dimensional problem, okay, multi-dimensional problem. So in this lecture we will discuss about such type of problems and what are the techniques of optimizations for a multivariable functions. So this is basically multidimensional function is basically multidimensional unconstrained function or minimization refers to the process of finding the minimum value of a real valued function of several variables without any constraints on the variables. So formally given a function which is consist of n number of real value, and then we need to the value of these parameters. This x consists of a set of say x1, x2 and so on. It consists of so on, and as it is a multivariable function, then we need to take the value of this one partial derivative, and there is no equality or unequality constraints. There is no constraint as it is not a constraint optimization techniques. So this we need to take this argument of this because of the fact say this one say a function is consists of say for example a function is consists for x1, x2, x3 and so on xn and then we need to take partial derivative of the function, like in a single variable function we need to take delta f by delta x1, we need to take delta f by delta x2, we need to take delta f by delta x3, right. Now, so on, and if it is like the single variable function, you need to take this one is 0, this one is 0, this one is 0. In matrix form, it can be written in matrix form, this the same thing can be written as delta f delta x1 delta f delta x2 and delta f x3 and so on. If it is a 3 variable function, this one is called and like the single variable function, all of these are this should be 0, and this one is a single term, it is called nabla g, that means this is called a gradient vector. Okay, that is called gradient vector, right. This is called a gradient vector. This is so this is the primary gradient based optimization. We are talking about gradient based optimization. Of course, there are other methods for optimizations also there, we will discuss in later units. The problem, this function at this is basically a multivariable function. So, you can expect that this function will be nonlinear and continuous in nature. Nonlinear and continuous in nature means this function is basically something like that. Okay. And it has some global maximum and some global minimum value, that means say this one is local minimum, I can call this one is a local minimum, local maximum value I should say, and this one is called, of course this one is called global maximum value, So, and this function may be smooth or gradient exist, or function may be non smooth also, that means discontinuous in nature. Then these techniques for gradient based optimization technique will give you not a very good result, rather a poor result. Then some other techniques should be used. So in a single term, for a multivariable function, we take the gradient vectors of the functions consisting of all of the variables, more specifically partial derivative of all of the variables, and we put this 0, and all of these things from these we take the value of argument of all of these parameters, argument of all of these parameters, argument of all these values, right. And again there are some classifications is also there, some of them are we will discuss later on. We will discuss this method in the lectures, this gradient based and first order, that means for multivariable function we will use this also. There are some examples also and other examples also, Nader mid simplex method, pulse direction set method, pattern search method. There are many techniques in optimization, of course. These are called derivative free or zero order methods. Both used the gradient and Hessian matrix for faster convergence of near minimum value of this, that means Newton's method, quasi-Newton methods, Levenberg-Marquardt methods for least squares methods also there. What we have discussed? We discussed here gradient of the function first, then this one steepest ascent or descent. Of course, this technique we will use in a separate video. We call it steepest descent method. And like single variable function, we calculate the Hessian matrix also. So what we have done in single variable, for checking the maximum value or minimum value, we have calculated double derivative of the function. Like this, we will calculate the double derivative of the gradient matrix. We call it basically Hessian matrix, basically this one, d dx d dx is equal to Hessian matrix. Okay. And in some of the methods we will discuss about the how to calculate this one. This is basically called line search methods. Line search methods, and we calculate the step size of the line later on. In this, in SDM, in steepest descent method, we will discuss separate video. Okay, it is called step length. Okay. Step length. So in this lecture, what we have discussed? We have discussed separate type of optimization techniques. This particularly we have discussed about the techniques for optimization of multivariable functions. The basic techniques is that we calculate the partial derivative of each of the variable of the functions, and this partial derivative of each of the function consists of a gradient vectors. This gradient vector, we put this gradient vector is 0, and we calculate the argument of the gradient vectors, and then this is the value of the parameters or variables which inculcates the maximum or minimum value of the functions, and we calculate the Hessian matrix of the gradient vectors, and to determine whether it is minimum value or maximum value. The disadvantages of this technique is that you can sometimes you can reach a local minimum value, you can trap into local minimum value. So there are techniques also, several techniques, some advanced techniques are there to avoid the local minimum value of the functions. We will discuss some of the techniques in this course later on. I invite you to join my next lectures. Till then, goodbye.